Okay, hello everyone. My name is Mariola Ndrio, and I'm a PhD student working with Professor Sauer and Professor Bose, and my research focuses on electricity markets. This presentation today will be about electricity interchange schedules among interconnected power grids, and more specifically, I'll discuss purely market-based mechanisms, such as coordinated transaction scheduling, which is frequently employed in ISO-driven markets in order to determine the power transfers across an entire interconnection. Thanks. So in this slide, this map shows the regions in North America where an independent system operator has been established with the purpose to monitor and control the bulk power grid and its resources, as well as to administer wholesale markets for electricity. The geographical footprint of a system operator can be that of a single state, such as in the case of New York or California, or can span over multiple states, such as in the Midwest region we are, where the control is under the Mid-Continent Independent System Operator. Although each area is operated independently, however, the underlying grids are interconnected. That means that at every moment power flows from one area to the other via transmission lines, which we typically refer to as tie lines. Tie lines are very valuable transmission facilities, not only because they allow a large amount of power to be transferred from one grid to the other, but they also enable us to harness geographically dispersed renewable resources and overall to achieve a more efficient and seamless operation of an entire interconnected grid. So I'm going to focus only on parts of the grid, as I said, that are operated by a system operator that have also wholesale markets for electricity. In those particular parts of the system, the current practice that is employed in order to determine the optimal flows on the tie lines, it's a market-based mechanism which is referred to as coordinated transaction scheduling, or CDS. CDS, as I said, is purely market-based, and it relies on external market participants that are willing to trade across an interface that connects two grids. For example, they're willing to buy power. They want to buy power from one market and sell it to the other market, and the profit is the difference between the two buying and selling prices. One alternative to this market-based scheme, one could possibly envision a scheduling mechanism that does not rely on market participants, but it rather has the two system operators to coordinate by exchanging appropriate information in such a way that they perform a joint economic dispatch of the resources on both grids altogether. In other words, they optimize the flows on the transmission lines, on the tie lines, in the same way that they optimize the flows internally. However, this theoretical alternative to the CDS, which is typically referred to as tie optimization, faces certain implementation challenges that are related to the fact that it's perceived to violate the financial neutrality or independence of the system operator. In other words, two system operators on neighboring markets cannot engage in a trade with each other and cannot assume a financial position in each other's market. Their role is to act as pure market facilitators of trade. However, in our work, we view the tie optimization method as a useful theoretical benchmark against which we are interested to compare the CDS market outcome, particularly when taking into consideration the strategic behavior of CDS participants. So how do these mechanisms actually work? Essentially, in every case, the two system operators, let's consider a simple two-area interconnection, each of them operated by a system operator and connected through a tie line. For every case, the system operator has to compute a so-called supply stack, which basically gives how the locational marginal price at the border of each area varies with respect to varying amount of flows on the tie line. And in fact, this is much better explained through a simple diagram. Let's take a snapshot of that system for a certain period, at a certain period of time. And On the vertical axis, what I'm showing over here is price, dollar per energy, and on the horizontal axis is net power flow on the common tie line between the two areas in every direction. At a certain point in time, the system operator in area A computes the supply stack at its border by solving an area-wise economic dispatch, parametric economic dispatch, by varying the amount of power that flows on the tie line. Similarly, operator in area B performs exactly the same calculation and constructs the one is a red curve, the other one has a not very clear color. However, the supply stack of area A represents the incremental dispatch cost for the area A to supply more and more power towards area B, while the other curve represents the decremental cost of reduced supply to the system operator in area B as more and more power flows from area A into B. So the theoretical optimal would be where the two supply stacks cross, or in other words, where the total dispatch cost of area A plus the total dispatch cost of area B are minimized. The CDS, so this is the theoretical optimum schedule that these two areas should trade. However, the market-based mechanism, which is CDS, as I said before, relies on market participants to come in and submit trade requests or transaction requests to trade from one area to the other. And in fact, this happens through something called an interface bid, where each market participant has to reveal to the system operator what is the maximum amount of transport that they're willing to transact, what is the minimum price spread that they expect between the two markets, and also what is the direction of the trade from area A to B or B to A. The system operators then pool this entire information, the so-called interface bids, to construct an interface supply curve, which essentially represents market participants' willingness to trade across the interface. And the supply curve is cleared against the price spread between the two areas, which is the difference between the two supply stacks. The intersection point between the interface supply curve and the price spread is where the schedule of the CDS, the market-based mechanism, is determined. One thing that is important to emphasize is that these market participants in the CDS mechanism bear no physical responsibility on the delivery of power. Their obligation to this market is purely financial. It is the system operator's sole responsibility to dispatch resources in every area accordingly, such that it satisfies the clear transaction requests that have been determined in the CDS market. And because they bear no physical responsibility of the delivery of power, often this type of participants are referred to as virtual bidders. And virtual bidding, this type of bidding is many times referred to as virtual bidding. So virtual bidders essentially can fulfill a role similar to capacity-constrained generators that are competing to supply an elastic inter-area demand of transport. Can we? Oh, thanks. An elastic inter-area demand of transport, which is given by the price spread between the two areas. That price spread represents a relation between quantity to transport with price. So since we are interested in analyzing the strategic interactions of these players, this analogy motivates us to be inspired by prior work that has been done in game theoretic analysis in wholesale organized markets for electricity. So let us consider a CDS market with a collection of n participants. From now on, I will refer to them as players. And if I assume that the dispatch costs in each area are quadratic, then the inverse elastic demand of transport from one area to the other at the interface can be expressed as a linear function of the price given by given that by the expression in 1, where P denotes the price spread. And recall that I said that the theoretical optimum is at the point where the two supply stacks cross, or otherwise when the price spread between the two areas becomes 0, and it can be calculated and given by the expression 2. So our goal is to contrast the market outcome of the CDS by taking into account the strategic behavior of the players with respect to the outcome, to this theoretical optimum. We consider a transport offer structure for each player I, such that every player provides a non-negative parameter theta I to the system operator, with the understanding that she is willing to transport up to a maximum quantity QIP, given by the expression 3. And in this diagram, you can see with the blue curve how the values of the parameters theta I and Ci impact the shape of the transport offer. More specifically, the player I is willing to transport up to a maximum quantity Ci at a minimum price spread specified by theta I over Ci, and the more and the price difference required increases, as you can see, with the quantity or with the transport, and it approaches infinity as the latter approaches the limiting value Ci. So essentially, Ci can be viewed to express or to encode each market participant's budget constraint or to reveal their liquidities. Also notice that our parametric transport offer is a smooth approximation to the one that is employed in practice, and it's been inspired by supply function competition models that have been introduced recently in a line of literature and have been shown to have very nice properties, such as they support competitive equilibria, but most importantly, they've been shown to have a bounded price of anarchy. In other words, the inflation to the aggregate cost when the players act strategically with respect to the socially optimal cost is bounded. So given the collection of the transport offers by the end players, the system operator acts to clear the CDS market by solving a social welfare, by maximizing a social welfare objective given by the expression 4, where the transport offer of every player has entered the objective in the form of induced costs. Also notice that the induced costs have a form of logarithmic barrier functions, which also ensures that the cleared quantities from the market to every participant will be non-negative and less than or equal to their maximum liquidity Ci. So the goal of the system operator is to determine the individual reward, optimal reward to each player, which is given by the vector x, and the collection of all the sum essentially of all the individual quantities rewarded to every player will essentially determine the timeline schedule in this market mechanism. So the transport reward that is that results from the CDS market clearing as well as the CDS schedule are both functions of the strategic variable theta chosen by the players as well as their liquidities. The end players in this market, they act as suppliers that compete to satisfy the inter-area demand between area A and B, and they are essentially, their goal is to maximize their payoff, which can be expressed as essentially the price spread that is realized at the CDS schedule multiplied with each individual reward of the market participant, and it can be again expressed as a function of the strategic variable theta and the liquidities of the players. So in this way, we can go ahead and define a game, the CDS game, that constitutes of the set of the end players, the strategy space theta, and the payoff structure of each player. And what we are after is to find an offer profile, theta A ni, that constitutes a Nash equilibrium of the game, in the sense that at that profile, the payoff of every player is maximized given the actions of the other players. Or in other words, at that theta Nash, none of the players has any incentive for a unilateral deviation.
There's a very interesting paper by Roche Talukdar. He used to be at Carnegie Mellon. He got real old. I think he was over 50. He retired. But he had a paper on the Nash equilibrium that you can change the outcome with regulations.
Oh.
And he claimed that in the paper that the regulations improved the condition of the outcome of every player. So in other words, if you don't have any regulations,
Okay.
each person will fight and destroy each other.
Uh-huh.
And everybody loses.
Yes.
It's only when you have some serious regulations on controlling what the players can do you get a Nash equilibrium where everybody wins. So if you want to see it, I can give it to you.
Of course, absolutely.
Every time I see people talking about that, I always remember that paper. And I'm not sure what it's good for. It sort of it says that regulations are good, not bad.
Yeah, interesting.
Some people think regulations are bad.
Yeah, this is a heavily regulated area. I mean, the reason why we're, like I said in the beginning, is policy issues that do not allow the straight application of the tie optimization method, that theoretical, that because it runs counter the financial neutrality of the system operator. So we are after theta Nash, and a profile that no player has any incentive to deviate from that. And we have the following theoretical result. First of all, the CDS market, the CDS game always admits a Nash equilibrium, and moreover, if we assume that the liquidities of the n players are distinct, with Cm denoting the player, the maximum liquidity, then if every n-1 players have sufficient liquidity to supply the maximum demand, then the theta, the Nash equilibrium is at 0, and the CDS schedule coincides with a theoretical optimal. So basically what this says is that when every set of n-1 players, when no single player is pivotal in this market, and there is sufficient liquidity, then what you would get is the outcome under perfect competition conditions, when every player is price taking and nobody chooses their actions as if anticipating the market outcome. However, when that condition is not satisfied, then the player with the maximum liquidity emerges to be the pivotal player in the market, and more specifically, he is also the marginal player in the CDS market and the one that beats a non-zero theta, while every player that is inframarginal and has a lower liquidity in the market beats theta equal to 0. And in that case, the CDS mechanism will yield a different schedule than the theoretical optimal, and actually the difference will depend on the liquidity, half the liquidity shortfall in the market. Questions? Okay. So what basically this result shows is that the incentives of this design mechanism are in line with that of our theoretical method of tie optimization, and actually the CDS market would lead exactly the same outcome provided there is sufficient liquidity in the market. However, when that is not the case and we have an illiquid market, then the CDS schedule will be different than our optimal, and their difference will depend on the liquidity shortfall. And the player with the maximum, that has a maximum liquidity, appears to be pivotal. By the way, this result also has a unique equilibrium when all the liquidities are distinct. The equilibrium is still unique when all the liquidity, when there are multiple same liquidities between every player except for the player with the maximum capacity, but multiple equilibria can arise in the case when we have multiple players with maximum capacity. Do I have time to go through the proof? Okay, so basically the proof relies, I'm going to just describe very broadly the steps. The first step is that going back to the CDS market clearing, we can establish that the objective function is a jointly concave, and therefore the CDS market outcome admits a unique solution, which is given by the expression 7, that gives essentially the reward, the optimal reward from the market to each participant. And from that, we can compute the CDS schedule as a function of the actions of each player. And we can also compute the payoff of every player that anticipates the market outcome as a function of theta and theta I. The existence of the equilibrium is guaranteed due to the fact that the payoff function is concave in theta I, and furthermore, theta I can be shown to vary inside a compact set, and therefore that those two together guarantee the existence of a Nash equilibrium. And furthermore, if we are in search of, if we want to fully characterize the equilibrium, then taking into consideration the equilibrium conditions and the fact that the first derivative of the payoff for the player with the maximum liquidity is greater than the first derivative of the payoffs of every other player, then it's not hard to show that every player but the maximum player will end up beating 0. And in the case where n-1 players have sufficient capacity to supply, sufficient liquidity to supply the maximum demand, then the marginal player will also end up beating 0. And only in the case where n-1 players cannot supply the maximum demand, then the m player will beat a non-zero theta, given by the expression 12. However, the Nash equilibria predict the market outcome under a sort of idealized condition. That means that the actions of the other players are given, and furthermore, the players know the inter-area demand function, how it varies with price. However, that is not how players bid in reality. In most markets, bidders, they learn how to play over time, and they find basically they have update mechanisms depending on their history of rewards and of their bidding strategies. So in order to see whether under these more realistic cases we can have findings that corroborate what we saw from the Nash equilibrium, we decided to adopt a very simple update mechanism on the strategic variable of the players, theta I, where essentially every player increases or decreases theta I proportional to her liquidity, depending on her payoff over a certain period of time. We also constructed an inter-area demand function by looking at CDS schedule data between ISO New England and New York ISO, and also price spreads in the actual CDS market between the two areas. We assume that every CDS participant is agnostic to the actions of the other players and just use the previous updating rule in order to determine their strategy. And we consider two cases. The one is with a liquid market and one with an illiquid market. And what we found is that indeed when the market has, if we compare the outcome under low and high liquidity, indeed the price spread stays very close to 0 most of the times when the market is when the market has high liquidity, while it is much higher, it has long recursions away from 0 in the case of low liquidity. And similar, the QCDS and the ratio of QCDS over theoretical optimum stays closer to unity in the high liquidity case compared to low liquidity. So what we've shown here is how a game theoretic analysis of the market-driven CDS reveals that its incentives are aligned with the purely system operator-driven tie optimization method. Our preliminary simulation illustrates that higher market liquidity indeed improves the scheduling efficiency. In our future endeavors, we are keen to investigate how the uncertainty in the inter-area demand affects the Nash equilibrium and the market outcome, and furthermore, explore more sophisticated learning strategies for the CDS participants. Any questions? That's good. Thank you.
I can introduce myself.
Saying that Chris and I are the only two people in this room that have been to Socorro, New Mexico.
That is a fact.
If you're not familiar with Socorro, where the VLA is, and if you're not familiar with the VLA, you didn't see the movie Contact. Looks into deep space. It's in Socorro. It's 8 miles, 3 directions. The Earth rotates.
Something like that.
It's like a 24-mile dish. So it's an amazing device. It was designed by the guy that hired me. But he had trouble with his car there, so I helped him with that. So anyway, Chris worked his way here, and he's going to get his master's degree shortly.
Yes, well, thank you. My name is Christopher Sain. I have been to Socorro, New Mexico. It is a very exclusive club. If any of you would like to join someday, just fly on down there. My advisor is Professor Pete Sauer, and today I'll be presenting an OpenDSS implementation of a generic municipal microgrid for co-simulation. Just a brief outline of what I'll be talking about today. First, just a little bit of motivation. Secondly, I will go over what OpenDSS is, first of all, because I'm sure a lot of people here haven't even heard of it, and why it was chosen for this particular application. I'll then go into the microgrid itself, followed by some examples of simulations that we've run after some different modeling strategies. Then finishing up with an application that we've used this approach with the ARPA-E nodes group. This would be in conjunction with Professor Alejandro and his students, before just speaking to the continuing work. So most or many power systems research questions can be solved via deployment simulations. However, in real-world problems, oftentimes the full dynamic modeling can be too computationally intensive or excessive. It may not be the best approach. OpenDSS provides a way to model a system like that without dynamics, hopefully being able to speed up the process, make it a little bit easier on the hardware. It also has extensive co-simulation capabilities, which I'll talk to in a minute. Specifically, the application project I mentioned earlier, the grid model has to be able to interface with the Typhoon Hill, which if you haven't seen it is in the lab right down the hall. So it needs to be able to interface between different hardwares during a simulation. And we would like it to be based on the Ameren, Illinois Technology Application Center, or TAC microgrid that's local here in Champaign. Just going over a little bit of what OpenDSS is. It's free software, open source, and it's a frequency domain solver for power systems. The real bonus here is its extensive co-simulation framework that it has. For all intents and purposes, it gives you a library that you can use in programming. So you can use it pretty much with any language that you would think to use: MATLAB, Python, C, all of those. In this work, it's been done in Python, or in MATLAB. A little bit in Python, but that's not being presented today. It also has the benefit of being able to model balanced and unbalanced systems. Something like a power world, per se, only really gets into the imbalance during fault situations. And it does have this lack of dynamics, which makes it very fast and therefore can be run in the time between simulations in, say, the co-simulated system. However, we can get around this a little bit, which I'll talk to later. So the microgrid itself, what is it? This is, again, inspired by the Ameren TAC. So what do we have? We have 69 kV infinite bus in this model, which is the bulk grid. It comes through a modeled impedance down to a transformer here where it's stepped down to 12.47 kilovolts. Again, through an impedance down here to the substation at 12.47 kilovolts. We have 4 different energy sources in the system. We have a solar array, we have a wind turbine, we have some battery storage, and a natural gas generator. These are all generating at 480 volts, being stepped up to the 12.47 kilovolts. In terms of loads, we have a couple of neighborhoods attached to the microgrid, totaling about 200 homes. These are connected to the substation via a tap changing transformer. And then finally, a control building that's located on site. It's just one more load. Just a little bit of details about the things I just mentioned. The solar array has a maximum power output of 125 kilowatts. The wind turbine, 100 kilowatts. The battery storage, 250 kilowatts, and it's rated for 500 kilowatt hours, so 250 kilowatts for 2 hours. The gas generator, 1,000 kilowatts. And the tap changing transformer for the neighborhood contains 33 taps, 12 above and below the center tap, for a total of plus or minus 10%. So initial steps taken during modeling. First, we need to just get it working, get everything connected together, get all the elements placed. And so to that end, we abstract a lot of things out. First of all, we make all the sources completely arbitrary PV buses, all the loads as completely arbitrary PQ buses. These loads are in the data being presented today. They are running off of synthetically generated data based on Patero and Lund's model for generating household electric loads. All the transformers are ideal and transmission lines are lossless. So here are just a few initial simulations based on this simplified model. Over on the left, you will see the generator outputs, and over on the right, you will see the power exchanged at the tie line. So this is power going between the microgrid and the bulk grid. And this is over the course of one day. Just to have something interesting happen, we have the battery storage here following a sine wave. This would not happen in practice. We have the solar and wind generators following some curves up here, and the gas generator just generating at its maximum capacity. The loads, which you'll see on the next slide, are what is responsible here for this power exchange between the grid and the microgrid. You can see if you look towards the center here, the microgrid is going back and forth between pulling power from the grid and pushing power to it. So
in the real world, those dispatch curves.
Correct. Right.
So I mean, right now you just pick them out of the air, right?
Right, this is just made up for now. Yes.
But actually, the cheap ones would be the ones that dispatch first and so on.
Correct. So moving on to the loads, we have, you can see the A phase, B phase, and C phase loads in the neighborhood. These have been artificially inflated for this demonstration just to show the effect of the tap changing transformer. So there are 3 different load models, and each load has been randomly assigned one of those models, scaled to a different value depending on the load. And then for this case, inflated to a much larger value in order to play with the voltage a little bit. So looking on the right side, we see just the A phase voltage at the tap changing transformer. See the voltage should be nominally 120 volts. We see as the load increases, the voltage here drops, and it seems it's very close to 120 volts over here, and then it drops down, and it really seems to get out of our acceptable zone. We see the red line, the tap changes. We were at tap 0 at the center tap, and we change up to the first tap. The voltage jumps back up here closer to the 120 volt mark. The load continues up until we see a spike in voltage, where the tap then returns back to center tap and the voltage drops down closer. So it's doing its regulation job as expected. Okay, so now refining the model. The generators will now follow more realistic curves. So this involves actual solar and wind data taken from stations in Decatur, Illinois, on July 21st, 1 year apart from each other, 2017 and 2018. The battery charges and discharges will now occur in a more realistic fashion, so not just some sine wave. The solar and the battery generators are now modeled, instead of as arbitrary PV buses just injecting power, they are now PV sources attached to inverters. And so the inverters injects a little bit of added complexity.
Chris, you gotta be a little careful. There are some people here that, when you say PV, they think you're talking photovoltaic.
PV meaning you specify the power and the voltage at the bus, so a generator. When you see, I think from this point on, when you see PV, it means power and voltage. The load values, they were artificially inflated before. They've been dropped down to more realistic levels, and the lines are now lossy. They're now being modeled taking the per unit length, resistance, inductance, capacitance from the IEEE 34 bus feeder. This is how the wind and solar are being calculated. Over on the left, you see the efficiency versus per unit power curve for the photovoltaic cell. And over on the right, you see the temperature curve for how much power versus nominal the cell produces with varying temperature. These both will come from the manufacturer of the device, and so they give you that this cell has a nominal value of 1 at 25 degrees Celsius. So the cooler it gets, it generates more power. The warmer it gets, it generates less power. And then these equations will dictate the power being produced. This involves the temperature, the irradiance or sunlight coming down, and this constant value here depending on the temperature. The turbine, the wind turbine, is being calculated using air density, area covered by the blades, velocity of the wind, and some efficiency factor. In this case, the wind turbines can never operate at above 59%. Some values were randomly chosen for the subsequent simulation. So these are some results using the refined models. If you look on the left, you'll see the different generation curves. Now, the generator has been dropped down to operating at a constant 500 kilowatts. You can see now the battery charges and discharges at different times of the day, coming online in the afternoon and evening to try to supply the additional load, while charging at night, while hopefully people are using less power. The solar, you can see the blue line here, peaks sometime during the day when the sun is at its highest point, which makes sense. And the wind follows, whatever the wind was like on July 21st, 2018. So we see again over here on the tie line, we are both exchanging, or we are pushing and pulling power to the bulk grid. However, it does look a little bit different due to this more realistic power curve. So looking again at the loads, they have been reduced down to the more realistic level, and we see that we no longer are seeing action on the tap changer because our complete voltage swing across all three phases is now less than 0.2 volts. So now just a little bit about an application that we've done with the nodes group. The nodes group is developing a distributed control algorithm to help use distributed control to control a microgrid to provide ancillary services to the bulk grid. In this case, frequency regulation. So they have algorithms, which you can ask them about, that calculate essentially 100 different power values for 100 different controllable nodes. They will then assign those power values to those nodes, simulate the network. They will get back the power that's exchanged on the tie line, and hopefully that power should be what they ask for. This is done using the C-Hill testbed, and the case I'm presenting now is trying to follow the PGM reg D wave. The reg D wave is just a 40-minute signal. It's used for making sure that the systems are following the specifications that they need to meet. This was done in collaboration with a group at the University of California, San Diego. They worked on modifying the microgrid to be a little bit more in line with what theirs is on their campus. But in implementation, it's pretty much exactly the same. So our target metrics for this simulation were to have a less than 5-second response time between reception of the signal and change in power output, and a reserve magnitude variability of less than or equal to plus or minus 5%. So that means when we're holding steady, we want to see our output power be within 5% of our requested power. So here you'll see the reg D signal coming in and the power exchanged on the tie line. Reg D in red, tie line in blue. You'll see that the reg D signal comes in first, and after about 4-second delay, it varies between simulations, usually between 4.3 and 4.7 seconds, you see the microgrid respond. And we see that for this, this was just manually inputting different values to test an increasing ramp. We see that the microgrid does follow the reg D signal as it should. Now we move on to the first 5 minutes of that reg D wave. This, what did you want? It depends between simulations anywhere from 4.3 to 4.8 seconds, because sometimes the distributed control takes a little bit longer to come to a consensus. Sometimes it goes a little faster. Did that answer your question? Okay. So now we have the first 5 minutes of the reg D wave. This portion was shown to showcase the downward ramp that you see towards the end of it, where we are still maintaining the 5% between the reg D and the tie line all the way through. And now we have the second 5 minutes, which is to show a steeper upward curve. The lines over here on the right, or the bars, indicate plus and minus 5%. So because the tie line power exchanged is within those bars on the reg D line, we are meeting the plus or minus 5% spec. Any questions about that? Kind of went through it a little bit fast. Okay. So just some continuing work. This is almost done now. Just a few more things to add is adding swing equation dynamics to the model. Now, I said OpenDSS doesn't have dynamics, so what am I talking about? Because we're driving OpenDSS through different software, in this case MATLAB, you can implement these dynamics in MATLAB and then just feed the updated values into OpenDSS, and it will calculate it in steady state in OpenDSS, but you're giving it dynamic values. We would also like to integrate the model directly into the Typhoon Hill. Right now, we have a separate computer running OpenDSS. It communicates over the network to the hill and then back, which does add some significant delay to the simulations. We know that it is possible to implement OpenDSS on the Typhoon Hill. That's just something we need to do. So that will eliminate our communications bottleneck. And finally, while this grid is really for co-simulation purposes in being controlled by something else, we would like to implement a governor controller on the gas generator within the model, just to see if we can run some simulations entirely in the OpenDSS framework and have them still be meaningful. Are there any questions? That's all I have.